Today we're going to talk about alternating current circuits. You'll notice that alternating current circuits are used in a lot of ways in your appliances in your household, all kinds of applications for AC currents and AC sources. We'll also be talking about transformers and power transmission, and at the end we'll talk a little bit about electrical filters before we go on. So, very simply, an AC circuit consists of a combination of current elements, power source, but in this case the power source is going to have an alternating voltage. We'll call it little delta V. Oftentimes we're going to use lowercase symbols for instantaneous values, and then the capital letters will indicate fixed values. That's where we're going to differentiate between the two when we do AC circuits. Start with AC voltage. We know that AC voltages from a power source are sinusoidal in nature. They'll vary in time as some delta V max times sine omega t. Delta V is going to be the instantaneous voltage. Capital delta V max is going to be the maximum output voltage for the source, or sometimes what we call the voltage amplitude. Omega would be the angular frequency for the source. We can calculate the angular frequency as 2 pi times the normal frequency, or 2 pi over the period of the source. Period, of course, is the time between, let's say, two successive peaks in the cycle, or two successive troughs. The voltage is going to be positive during one half of the cycle. It's going to be negative during the other half of the cycle. That's the way AC circuits work. And so the current in any of these kinds of circuits, if I have an alternating voltage, I'm going to have an alternating current as well. In the United States, we use a frequency of 60 hertz for alternating current, which corresponds to an angular frequency multiplied by 2 pi. That's 377 radians per second. We'll start really simply. Let's put a resistor in an AC circuit. So I've got a alternating source. You see this squiggle in here indicates that it's an alternating voltage, regular old resistor. And in fact, resistors, as you'll see, behave pretty much in AC circuits the way they do in DC circuits. So over time we have the voltage is going to be Vmax times sine omega t. And of course delta V sub r would be the instantaneous voltage across the resistor. So a very simple circuit with just one resistor and a voltage source. We can write the instantaneous current in the resistor as just, again using Ohm's law, the voltage at any time divided by the resistance. And so we could write that then as I max times the sine of omega t. We could also write the instantaneous voltage across the resistor as I max times R times sine omega t, where I max would just be delta VR over R. If I look at the graph of voltage versus time as opposed to resistance versus time, I see a trace that looks the same. I see curves that have different peaks. The current may be different, a different value in the voltage. That wouldn't be surprising. But I see that they are in phase. The peaks for when I have a resistor in the circuit happen at the same time. The current and voltage peak at the same time, they have troughs at the same time, and they have zeros at the same time. That's always the case for a resistor. So in other words, the direction of the current doesn't in any way affect how the resistor behaves. So that's why I said before, resistors in AC and in DC circuits by themselves behave in exactly the same way. One of the things that we do to analyze AC circuits is to employ phasor diagrams. These are a little bit confusing at first, but they turn out to be pretty useful. What's happening is the length of the phasor, the vector, so to speak, is going to be equal to or proportional to the maximum value that it represents. And we have this thing rotate counterclockwise around this graph to indicate that it's changing over time. The x-axis generally means nothing. It doesn't correspond to anything. The y-axis corresponds to the amplitude of the signal, whether it's a voltage or a current or whatever the case may be. And so, and we say it rotates at some value omega, which is the angular frequency associated with whether it's current or voltage. Notice that in the case of a circuit with just a resistor, the current and voltage are both pointing in the same direction. One may be larger than the other, but they continue to stay in lockstep as the frequency changes. In a sense, we can look at a phasor kind of like a graph. We're going to see that we have time on the, if I had a rectangular representation, I might look at voltage on the vertical axis and time on the horizontal axis. And then I would draw my phasor as it would be in a polar coordinate type of graph paper, where the radial coordinate represents the amplitude of the voltage, and the angular coordinate shows us the phase angle. And in this case, the vertical axis is always the amplitude or instantaneous value of the voltage. Horizontal coordinate doesn't represent anything. We'll do the same thing. We can do this for voltages. We can also do this for currents. And that's a nice way of pictorially representing AC circuits. Now, if I have a current, an alternating current in a circuit, on average, the average current is going to be, in one cycle, will be 0, because I have just as much negative as I do positive. So we often tend to look at not just an average current. We're more likely to use something called the root mean square current, or RMS current, for an AC circuit. And the RMS current is simply the maximum current that you can have divided by the square root of 2, or 0.707 times the maximum current. We can also write voltages as RMS voltages, where we take the maximum voltage and divide by the square root of 2. Same way. So RMS, we'll remind you, is root mean square. Oftentimes, when we're talking about voltage or current measurements, we actually mean the RMS value. So for example, if I have an AC source, and let's say I have a voltage output that looks like delta V is equal to 200 times the sine of omega t. And I would like to find the RMS current. Suppose I'm connected to a resistor that is equal to 100 ohms. And I want to find the RMS current. That would just be IRMS is equal to the maximum current divided by the square root of 2. In this case, the maximum current would be 200 over 100, because maximum value for sine is 1. So it would be 200 divided by 100, or 2. So it would be 2 over the square root of 2, or 1.41 amps. That would be my RMS current. So it's a very simple example of how to use RMS in a circuit. We're talking about power in a circuit. Of course, the rate at which electrical energy is delivered, it's traditionally been I squared R, where I is the instantaneous current. This is not going to be the same, though, as the case where we have a DC current, because the maximum current is going to only occur for a short amount of time. Therefore, we're more likely to talk about an average power in terms of an RMS current. So my average power then is going to be equal to my IRMS squared times the resistance, instead of the maximum current squared times the resistance, as you would see in a DC circuit. Typically, ammeters and voltmeters, when I'm doing AC measurements, are going to read RMS values. And many of the equations that we use will look a lot like the DC equations, which make things, makes things a little bit easier for us. Well, with that in mind, let's step on out to a more interesting, or more, at least a different circuit element. That is an inductor. Suppose I have an inductor in an AC circuit. If I apply Kirchhoff's loop rule in this case, notice I have a derivative in this case. It's not a constant like a resistor. I'm going to find that my maximum voltage goes as sine omega t. But what will happen then for the case of an inductor is the current is going to be V over L sine omega t integral. So when I integrate to get the current in an inductor, what I get is a cosine function. Or if you like, a sine of omega t minus pi over 2, if you will, for the current. What that means is that the current and the voltage are out of phase. In this case, what we say is that the current lags the voltage in a circuit with inductors by a amount of pi over 2 radians, or 90 degrees. So this is the first we'll talk about a very simple saying that we have for AC circuits. The first part of the saying is Eli. So for an inductive circuit, the voltage leads the current, and it's by 90 degrees. So keep that in mind. When we do capacitors, it will be just the opposite. This being the case, you can see if I were to graph the voltage versus the current, you see how the voltage here is 90 degrees out of phase with the current. See the peak in the voltage occurs ahead of time of the current, so they're not in sync at all the way they are when you have just resistors in the circuit. We say that the current in the circuit lags behind the voltage by 90 degrees, or if you will, the voltage leads the current by 90 degrees. We can draw a nice phasor diagram for an inductor, because now you can see that they're not along the same line the way they are in the case for resistors. They're 90 degrees apart. Here's my voltage vector or phasor. Here is my current phasor, and you can see there's 90 degrees in between them. So just another way of showing how this works. Inductors provide a resistance, so to speak, in a circuit. There's something about inductors that resist the flow of current. And we measure that in terms of something we call reactance. Factor omega times L is defined as my inductive reactance. We call it X sub L, or some texts use capital Chi sub L to mean the same thing. And it's just, omega times L is just, essentially the units are going to be ohms, just like resistance, and it's a measure of how much the inductor resists the flow of current. We can express the current in terms of inductive reactance in the following way. We can write it as delta V max over X sub L, kind of like an Ohm's law where we would have resistance in the denominator, or IRMS as delta V RMS over X sub L. And you can see as the frequency increases, the inductive reactance also increases. You see the connection with Faraday's law. Larger the rate of change of current in the inductor, the larger the back EMF, the higher the reactance. And of course a decrease in the current. So we see that this all works together with the fundamental law of Faraday. We can do a very simple example of that. Suppose I want to calculate the inductive reactance and RMS current for a purely inductive circuit. I can do the following. I have a voltage source, and here's my inductor. Suppose my voltage source is 150 volts for VRMS, and my inductor is 25 millihenry. And suppose I have a frequency of 60 hertz. Suppose I want to calculate my inductive reactance. That's equal to omega times L. So that's just going to be 2 pi times 60 hertz. times the inductance, 25 times 10 to the minus 3 henries, and that will give me 9.42 ohms. Notice we get a unit of resistance when I find an inductive reactance. My RMS current for a circuit like that would be equal to my VMS voltage, 200 volts, divided by 100 ohms, square root of 2, and that will give me 1.41, I'm sorry, that will give me, let me write that again, 200 volts divided by my inductive reactance, 9.42 ohms, we said it's 150 volts, sorry, is equal to 15.9 amps. So that would be my RMS current for a purely inductive circuit such as this one.